Okay, so this is section 2.6, toolbox functions and transformations. So a toolbox function is essentially like the parent graphs, and we'll talk about what a parent graph really means. So when we look at a parent function, what that can mean is it's a basic version of a function that shares characteristics with some more complicated functions of the same type. So same type means same degree, same format, etc. Those same type of things. So in this one, we see the identity function, which is, we just call that identity because it's just y equals x. It's very simple, basic function that everybody can work with and know what it looks like, right? It's just a line going through the origin because it has regular slope of 1 and it goes through the origin, like we said, with a 0 y-intercept. So if we look at this, right, we see that we have certain things showing on here, right? Like we said, we have the origin and a slope of over 1, up 1. So with that, we can always find just a chart of our values and plot from that if we're ever unsure of what a function looks like. Now, just a few things about the identity function. It has domain of everything, meaning, well, what can we plug into y equals x? Every x is valid there, right? We can plug in negatives, we can plug in 0, we can plug in positives. There's nothing that doesn't work. Okay, and then if we think about it, when we plug in those things, what do we get? Right? So, well, let's think about that. If we plug in negatives, well, y equals x, so we get a negative. If we plug in 0, we get 0. If we plug in positives, we get positive. So, again, that means the range is all real numbers, or negative infinity to infinity. Then again, remembering from a previous section that the symmetry is odd because we can turn it around, upside down kind of thing, right? And it'll look the exact same function. Then, if we look at this, going again, remember from left to right, that function is increasing on x, right? Now, then the last thing that we can kind of note is the end behavior. The end behavior, we do look at those in just what direction they're pointing in, okay? It's not a left-right thing. So end behavior, you just look at the direction that they're pointing. So the end behavior is down on the left and up on the right then. Okay, so then next one is a squaring function. So squaring function, that's just x squared. Okay, it's a basic quadratic, right? Again, going through the origin and having just a basic up 1 over 1, up 3 over 1, right? So you're just squaring each input. So again, thinking about the domain, you can plug in anything you want, right? Negative, 0, positives. However, when you plug those in, you don't get everything. Because if we plug in a negative, well, it gets squared and it turns positive. If we plug in 0, we get 0. But if we plug in positives, it gets squared and turns positive, stays positive really. So that means we don't have the full range. We just have from 0 included to infinity. So that means it just uses kind of the top half almost in a way. Now, thinking about symmetry, it reflects around the y-axis, right? So that means it's an even symmetry. Then, well, decreasing and increasing on this one, right? Remember from left to right, okay? So it's decreasing until 0 and then increasing after 0. And then end behavior, both ends are pointing up, so the end behavior is up for both. Okay. Next is the square root function. Just kind of following along, we squared it, now we unsquare it, right? So the square root function, you have to be careful with this, right? Because if we had started out with y equals x squared and then we're trying to kind of undo it, right? That would be the plus or minus square root of y equals x, right? Well, that's a plus, sorry. So the only thing is, if we had tried to plug it in like this, but with the y's and x's reversed, of course, well, that would mean that we would also have this part of the graph over here. That's no longer a function, right? Because it doesn't pass the vertical line test. So we don't have that, right? We just have the positive version of it, meaning it's a function, right? So we don't have to think about those things because we want to keep it in function form. Okay, so now let's look at this graph itself. We cannot plug everything in because we can't take the square root of a negative number. So this function is the first one that has a restricted domain, meaning you can't plug everything in, basically. We can plug 0 in. The square root of 0 is 0. The square root of positive numbers is a positive number. Might not be a nice number, but it's possible to do, right? We cannot plug in a negative number and stay real. We could plug it in and get an imaginary number, but we're plotting on the real coordinate plane, so we don't care about imaginary numbers for this function. So then, if we think about that, we plugged in 0, we got 0. We plugged in positives, we got positives. So our domain and our range are both restricted to only positive and 0 numbers. Then, let's think about symmetry. Well, it's not reflected about the y-axis. If we turn it around, it's not the same function. So this is neither even nor odd. So then if we look at it, it's increasing because we start here at 0 and then follow the graph, right? So it's an increasing function from 0 to infinity. Notice we did not include 0 because, again, we do not include endpoints. Then the end behavior. So this one, end behavior, it's only on one side. Even though technically the function has two ends, that starting point, what we call an initial point, we don't count that one. We just really talk about the arrows as being endpoints, or end behavior more or less than an endpoint, really. So the end behavior is only up on the right. Then it has that initial point at 0, 0. So then the next parent function is the cubic function, or the cubic function. So on this one, if we look at it, again, it's just the basic cubic function, right? We can plug in anything we want because, well, cubing something, we don't care, right? We can plug in a negative, we can plug in a 0, we can plug in positives. It doesn't matter, right? So domain is everything. If we plug in all those numbers, we get out all those numbers. So again, we don't care. Now, what about symmetry? Symmetry, if we flip it, right, around the y-axis, it's not the same. If we turn it all the way around, upside down, right, it's the same graph. So that means it's odd symmetry again. So then increasing, again, remember to follow from the bottom and then go up. So that is all the way increasing from the bottom to the top. Then end behavior, down on the left, up on the right. Okay, now there is this other thing that we talk about here at the bottom, point of inflection. We don't really talk about inflection points until calculus, but it's where it changes shape. Okay, it's this point right here at the origin, right? If we notice, this part kind of looks like it's kind of scoop down a little. This part kind of looks like a scoop up. That's what we mean by inflection. It changes shape from kind of scoop down to scoop up. Okay, it's just a change point. Like I said, it's not super important yet, but you will notice we're talking about it in calculus when you get there, if you have to get there. So then the next one, as we kind of would think, is the cube root function. So again, on cube, right, on any odd root, we can plug in negatives and be okay. So that means our domain is, again, everything, right? Our range, if we plug in negatives, we get out negatives. If we plug in 0, we get out 0. Positives give positives. So again, range is everything as well. The symmetry, if we flip it, it's not the same. If we turn it, it is the same, so it's odd. Increasing, again, following from left to right, is going up completely, so it's an increasing function. In behavior, remember this arrow is pointing down, even though it's kind of sideways really, it's still going down. Then this one is going up, so in behavior on the left is down, on the right is up. Again, this one has a point of inflection at 0, 0. Again, we won't talk about that really too much, just so that you know they're kind of there. Okay, the next one, it kind of changes ideas a little bit, is the absolute value function. So let's think about an absolute value for a second first. If we talk about an absolute value, what we're really talking about there is the distance the number had from 0. Okay, so basically we're thinking about on a number line, right? So we have 0 here and we have 3 here. Okay, well, that means that this distance is 3. Not that just arbitrarily right here is 3, just this distance from the 0 point is 3. So if we go over here and have -3, the absolute value is saying, well, what's this distance from 0, right? It doesn't say what direction the distance is in, so we don't assign a value to it, saying a sign to it. So this is still a distance of 3. So meaning basically an absolute value just measures distance, not direction. So that's why we don't care about signs with absolute values. So we can plug anything we want into an absolute value, right? Negatives, 0, positives, it's all good. So it's infinity to infinity. Then range, well, we plug in negatives, we don't get negatives, right? Because the absolute value takes the signs off. So we only get 0 to infinity. If we flip it, it's the same graph. So it's even symmetry. Then if we follow from left to right, it starts with decreasing, then increasing. So -infinity to 0 for decreasing and 0 to infinity for increasing. Then its end behavior is up on the left and up on the right. Vertex, remember a vertex is kind of the bottommost point or topmost point, could be upside down, right? It's just where the graph kind of starts mirroring itself, really. You only have that on even symmetry graphs. Or what parent function is an even symmetry graph. So that point right there is the vertex. Same thing on a quadratic function, would also have a vertex. Okay, so now what we're really talking about in this section are transformed graphs or transformations. Okay, so what you want to think about here is a few key things. You want to think about the function family. That's all those graphs that we just looked at. Is it a linear function, the identity function? Is it a quadratic? Is it a square root? Is it a cubic? Is it a cube root? Is it an absolute value, right? There's a few others that we didn't really talk about, but those are the main ones that we'll see. So basically decide which function we think it looks like if we have to go from a graph, or we can just say, okay, what's happening to x, right? What function does it seem like it is? Then we think about the domain and range. What are allowable things to plug in and what do we get out, okay? So that can change when we move or change a graph. Excuse me. So then the next thing is the vertex. Again, remember, we don't have a vertex on every graph. So that's kind of, we only sometimes think about this one. So this is kind of a sometimes, okay? Only on x squareds and what was the other one? Absolute values, right? So only on those do we have vertices. technically. Then the next thing is if the function would have a maximum or a minimum value. So we had those on a lot of the different ones. We have a minimum on the absolute value graph. We have a, we have a minimum on a square root function. We have a minimum on a square function, right? So we have kind of some of those different things on multiple of our family groups. But we don't always just have a minimum like we saw in the parent graph. Sometimes we could have flipped the graph around and now we have a maximum. Okay, so just be careful thinking about what's happening to the parent. So what changed? So then you can think about its end behavior. Which direction do we think the end should go in, right? Did it change or should it be the same as the parent graph? Then x and y intercepts. Those are always kind of good to think about because they can really give you some good points and really good kind of behavior. Like, okay, if I know my x-intercepts, I know where it is along the x-axis. If I know my y-intercept, again, I know how far up or down that portion or that point is. So let's think about kind of a graph like this. So if we look at this, well, we know this is a quadratic. So this parent function was the y equals x squared function, right? So what did we do to it then? Well, we moved it, right? We didn't, it looks like if we find the vertex right here, we still go up 1 over 1 in both directions, right? Then we went up 3 and over 1 in both directions. So that means we didn't change the function too much. We just moved it, right? It's still going up. It's still going up the same amount in each point, right? So what did we move it? Truly, we only really have to think about what did we do to that vertex. That's the thing we want to think about. So originally the vertex was on the origin, the 0, 0. So we moved it to the right 1 and then down 4. So right 1 and down 4. Well, how do we talk about that, right? How do we write that in the correct kind of format or easy format? Because to me, this does not go directly into knowing, oh, that's of course my function right there, x squared minus 2x minus 3, right? I wouldn't even think to know that, okay? There's middle steps to go into. So let's talk about different transformations before we get there. So the first one is a shift. When we kind of talk about a shift is those just moving it like we did and saw on that previous example. Moving it to the right or left, moving it up or down. So what those look like in a function, we'll kind of just be basing it on the identity function, but I will parenthesize so we'll know kind of grouping wise where things go. So we'll call it kind of with the better wording, right? Vertical and a horizontal shift. So with vertical shifts, that's the K, all right? So K is vertical, okay? So if we think about just on a graph right here, okay? For the vertical, if we have a plus K, well, it moves the graph here, right? Plus K. However, if we have a negative K, well, it moves it down, minus K. So every point that you know from the parent function just goes up or down K amount, right? Now, if we go and think about a horizontal, it's almost the exact same thing, just instead of on the y-axis, on the x-axis. So a positive h change, though, it's a little bit tricky. It doesn't go in this direction, okay? That's not positive h anymore because it does the opposite, okay? So it's a little strange to think about. What I want you to remember is if the change that you're looking at is with x, if it's with the variable, then it changes in the opposite direction. Now this applies to k, because k isn't with y, right? It's not with the f of x. So that means it does it in the real direction, right? We moved it and changed the sign to the opposite, so now it's really the direction, okay? So basically think it moves h in the opposite way, okay? Because it's with x. Or another way of thinking about it is, if we plug in x, well, to get the same x kind of value there, we have to change x by h amount, okay? That's a little confusing to think about. So let's write that down for a second. If normally I plugged in 2, well, and I have an h value of, let's just say 1, well, now I'm getting 3. So if I want 2, I have to change to plugging in 1, right? So now, instead of plugging in 2 to get 2, I now have to plug in 1 to get 2. So see how it changed it into the left when really it was a plus h value? So that means, like we said, it goes in the opposite direction. So it's no longer to the right for positive, it's to the left for positive h. And then to the right for negative h, okay? Just remember, if it's with x, it goes in the opposite direction. K goes in the real direction, okay? So that's a shift. Now the next type of transformation is a reflection. Reflections literally just kind of mirror the function across an axis, essentially, okay? So the first type is a vertical reflection. Vertical reflections, like we would think, mirror it vertically, right? So what that looks like is you are multiplying the entire function, the y, by a negative value, okay? So you're kind of doing it like this. Literally, it's vertically reflected. So that means up and down reflected. Vertical reflection is a reflection across the x-axis. Ooh, this is too early in the morning to spell for me. I'm sorry. Across the x-axis. So, if we look at this, it makes sense, right? We see the point right here just got moved down here. Point here got moved down here. Here, reflected across, moved here. And this one moved across and reflected down there. It literally, we had it here, we reflected it down, okay? So that's a vertical reflection. Now, a horizontal reflection. We kind of think what we already know what it looks like, right? But let's talk about the function first. This one, notice the negative is in the different place. Before, with a vertical reflection, it was in the kind of y, right? Because it's outside of f of x. That's y, right? Then now the negative is in with the x, meaning it's affecting the x first, okay? So that means it's changing the x's that you plug in, more or less. So that means, right, it reflects across the y-axis on this one. So this one is y-axis. Now notice, right, we had a point here, it reflected over here, point here, reflects over here. So they match up, it's just reflected with the same distance, almost kind of like an absolute value distance, just across the y-axis, or before for vertical across the x-axis. Okay, so those are reflections in both directions. The next type is a stretch and compression. So what that means is we can kind of have a basic graph and then we can pull it or we can press it so that kind of less happens in a certain distance or more happens in a certain distance, okay? So stretching is if A, we don't know what A is yet, but we'll talk about it in just a second. If A is greater than 1, okay? So that kind of makes sense because A is what goes out front of X, okay? So that's kind of if we have the function, let's think about just the identity graph again, y equals x. Well, A would be y equals ax right there in front. It's the slope in this instance, okay? We don't always have slope necessarily to talk about in the same way on other functions, but in this parent graph, A is just the slope. So if A is greater than 1, 2, well, we know that shifts the identity function to be steeper, right? It gets bigger quicker. We just stretched it, right? It gets to the same area or places, but just it gets there quicker. Okay, we stretched it out. Next is compression. Compressing is if A, that front number, is between 0 and 1. Think about what a number between 0 and 1 is, though. Between 0 and 1 is a decimal. Decimals, well, those are kind of like a different way of writing a fraction in a way, right? So basically, if A is 1/2, well, instead of multiplying your x values by 2 and getting bigger y's, right, you're cutting your x values in half. And so then you're not getting anywhere as quick. You get there, but not at the same time. It takes longer to get as high, right? So what these kind of look like is this, okay? So we have, notice, we have the same x values to plug in, right, for all three types. Then we have the parent graph of a quadratic. Then we have the stretch because A is 3. Then we have a compression because A is 1/3. Notice we used the 3 and the 1/3, so it's very similar. It's changing by the same amount, right? Either multiplying or dividing by 3. It's just which direction it kind of stretches or compresses. So when we change, right, to stretch it, we notice, right, that this point right here goes up. Same on this side. You get there quicker. However, if we compress it, well, this point goes down here. You don't get there as fast. You're lower at the same point that you were much higher at before, even from the parent graph. So that's kind of all of the different types of transformations that we can have. So let's list them back out. Now, we're also going to put them in the order that you have to think about them on, the graphs, and how you have to work through and change the function, okay? So the first one you want to think about is a horizontal shift, okay? Does it move left or right? Then you want to think, does it reflect? Does it reflect about the y? Does it reflect about the x? Does it stretch or compress? Then the very last thing you want to do is do a vertical shift, okay? Why that is, if you do a vertical shift first, well, then your reflection will not be done correctly, right? If we think about that, we have just a basic graph. Let's think about it like this, right? If we shift that, let's say we do a vertical shift up, so it's like this instead, approximately, right? Then if we reflect them, well, if we reflect it around the x-axis, right? Well, the black one, the first one, will reflect like this, and then shift up, right? So then its new one would be a shift up. So let's say it goes to here, right? So that's the kind of actual graph, is the one with arrows on it, okay? We had the first, we reflected it down, then we shifted up. That's the real way we're supposed to do it. But if we do the vertical shift first, we get the red one, right? Then we reflect it. Well, we have to take into account this distance right here. So it doesn't just reflect right here, right? It reflects down here. And those two graphs are drastically different from each other, right? So that's why we have to make sure to do it in the correct order, all right? You have to go horizontal shift, reflect, stretch or compress, then vertical shift. Okay, so how we kind of write that out? We know our basic kind of function is just y equals f of x. So to change that and kind of apply all of those different transformations, what our function looks like is this. Okay, let's again talk about what all those things mean. So the first one, so a horizontal shift, that's plus or minus h. Okay, then a reflection comes from a being positive or negative, not the a value. Remember, just if a is positive or negative. You will not always have a reflection. The next is a stretch or compression. That's just the a value itself, not whether a is positive or negative. We don't care. We just care what a is. Is it positive? Is it bigger than 1, or is it in between 0 and 1? Then last is a vertical shift of plus or minus k. All right, so those are the transformations that we can have. All right, so this is an example in Alex for you guys to kind of follow along with me, because I wanted to show an actual transformation and how it worked, and how to do it in Alex. It doesn't really help much if I just do it on a graph for you, but I wanted to actually use Alex tools and in the software itself. Okay, so if we look at this, the first one is wanting us to do, well, first think, what do we do first? Well, that was a horizontal shift, right? That means we deal with the minus 4. Okay, well, that means, what do we do? Well, minus 4 does not move in the direction we think. Remember, it's a horizontal shift. It goes in the opposite direction. That means minus 4, instead of going left, is going to go right. It's going to make points bigger. So what you want to do, draw out those points first. So it goes to the right 4. So this one goes to the right 4. 1, 2, 3, 4. Then this point goes to the right 4. 1, 2, 3, 4. The point that started here, the end point here, goes to the right 4. So 1, 2, 3, 4. Now, however, we don't stop there because that's not our last transformation. We also had a times 2. Now, the 2, remember, it stretches it vertically, right? Because it's bigger than 1. So, can we stretch something that's on the axis? If it has a 0 value coming out, can we stretch it? No, because it's 0, right? The only one we can stretch is this point right here. We can stretch it, or kind of multiply it in a way, by 2. So instead of being here at 4, we stretch it, multiply it by 2, so it goes up to 8. So we should take away this point now, because we stretched it, and then we pick this line tool here, place the first point, the second point, and then choose it again. First point, second point, and there's our function, okay? So let's now do the second one. So the first thing we should look at is, well, we do a horizontal shift, then we do a reflection. We have a reflection. This is a negative on the x. So which did that change? Did it reflect it about the x or the y? Well, remember, it goes the opposite of what you think. If it's with kind of the variable, it doesn't do it the same way, right? So negative is on the x, meaning it does not reflect it about the x-axis. It reflects it about the y-axis. So let's do that first. Now, if something is on the axis and we flip it, it doesn't change, right? So this one is still right there. This point is 2 over from the axis, right? So instead of going 2 in this direction, we're now going to go 2 in this direction, but on the same kind of up or down, right? Still on 4. Now this one is 4 from the y-axis. So instead of going in the positive direction, we go in the negative direction. 1, 2, 3, 4. Now that kind of here to here to here, that's our new function. But we're not done yet, right? We didn't do the vertical shift of -3. Now remember, a vertical shift does go in the normal direction of down 3. So all of the points that we had from the kind of intermediate step just go down 3. So this is 1, 2, 3, 1, 2, 3, and 1, 2, 3. Now remember to take away your original kind of intermediate points and then connect them with the line tool. Okay, so that is how we use Alex to do transformations. Okay, so that is lesson 2.6.